For this problem, you got to use the sum and differences of cosines to find the exact value of the cosine of pi over 12. Well, first I had to figure out what the heck is pi over 12. And so I used my old trick where I just let pi be 180 and divide that by 12, and I got 15. So we're looking at a 15-degree angle. Well, you have to use your 30, 60, 90 triangle and your 45, 45, 90 triangle. So I have to come up with either a sum or a difference that gives me 15. Well, I'm going to have to use 45 degrees minus 30 degrees to do this. So instead of the cosine of pi over 12, I'm going to have the cosine of 45 degrees minus 30 degrees. So I am essentially letting 45, and I'm doing this subtraction one, 45 is my alpha. So I'm going to need the cosine of alpha and the sine of alpha. And then I'm going to let my 30 degrees be the beta, so cosine of beta and sine of beta. So this is going to equal the cosine of 45 times the cosine of 30 plus the sine of 45 times the sine of 30. I'm going to erase this just to get it out of my face. Okay. But then I have to remember my trig stuff. So let's see. Here's my, if this is my 45, 45, 90 triangle, it goes 1, 1, and the square root of 2. And then if I draw this as my 30, 60, 90, the shortest side is across from 30, which will be 1. The hypotenuse is double that, which is 2, and then this side is 3. And so for each of these, let's see, here's my 30-degree angle there, and pick a, it doesn't matter which 45 you use, but anyway. When you go to do the cosine, remember that cosine is adjacent over hypotenuse. Remember, it's SOHCAHTOA, SOHCAHTOA, sorry, to T-A, TOA, SOHCAHTOA. Okay, so the cosine of 45 is the adjacent over the hypotenuse. Adjacent is 1, hypotenuse is the square root of 2. Then I come over to the purple, 30 degrees. Adjacent is the square root of 3 over the 2. Plus, and then sine is so, that's opposite over hypotenuse. So back to the yellow, 45. Opposite is 1, hypotenuse, the square root of 2. And then the sine of 30 is opposite is 1 and hypotenuse is 2. So I'm going to go ahead and do this multiplication here and this multiplication there. And I get the square root of 3 over 2 square roots of 2 plus 1 times 1 is 1. Square root of 2 times 2 is the square root of, or 2 times the square root of 2. And then since they have the same denominator, you can add the numerators and put it all over the same denominator. It's just that these are not like terms. I cannot add them together. And since one of them's under a radical and the other one is not, I tend to put the one that is not under the radical first and put the plus square root of 3 behind it, so I don't accidentally draw my square root sign too long and accidentally put the one under there with it. It's a personal thing. And then I went ahead and rationalized my denominator before I got my answer, and because because you have a square root in the denominator, I would have to multiply that times the square root of 2. But what you do to the bottom, you got to do to the top. So I'd have to do the square root of 2 up there also. What happens in the bottom is when you take this square root of 2 times that square root of 2, that's the square root of 4, but the square root of 4 is just 2. And then you still have this 2 right there, and 2 times 2 makes your denominator a 4. And then in the numerator, I'm going to have to distribute the square root of 2 times 1 is the square root of 2 plus, and when I took the square root of 2 times the square root of 3, you just multiply 3 times 2 and they're both underneath the radical. And that's what I got for an answer, and Mobius liked it because it gave me the green box. So there you go. They wrote the square root of 6 plus the square root of 2 all over 4. Okay, the only thing they did different is right here when I put the 1 plus the square root of 3, they left it as the square root of 3 plus 1. That's the only difference. Addition is commutative. It doesn't matter which way you add things, like 2 plus 3 equals 5, but if you reverse it, 3 plus 2, you still get 5. It doesn't matter which order you put them in. So my answer is correct.